Hello, welcome to part 2 in a series of videos on the latitude of the planets. What we're going to do here is we're going to summarize some key points about how planets move, and in summarizing it, it's going to put a lot of the pieces of the puzzle together, and we're going to notice some additional things. And then we're going to talk about how latitude is different between a geocentric point of view and a heliocentric point of view. So what is that mess on the left side of the slide? All those crazy looking circles. That's the paths of the planets. So we have the yellow circle in the middle is the sun, and we have this light blue or light purple color in the center. And what is that showing us? It's showing us the path of Mercury. And notice that the sun is not at the center of this path of Mercury, and the path of Mercury is not a perfect circle. It's what we call an ellipse, and this ellipse is stretched from this blue cross that I drew. And it says Mercury perihelion 17 Gemini 44. Mercury's perihelion is here. What is that? What is the perihelion? It's the point where Mercury is closest to the sun, and this orbit of Mercury is stretched from 17 degrees Gemini to 17 Sag. And when Mercury is at 17 degrees Sagittarius in the heliocentric chart, everything we're talking about here is heliocentric, Mercury is farthest away from the sun. And Mercury has a high eccentricity, means it's very elongated, as opposed to Venus, that has, which is, you can see in this light green circle, Venus, it has a low eccentricity, which means it's almost round. Now let's add one more thing I didn't talk about before, which is that when Mercury is at 17 degrees Gemini, it's moving fastest. A planet is moving fastest when it's closest to the sun. So when Mercury is at 17 degrees Gemini, it's moving fastest, and when it's at aphelion, the point farthest from the sun, it's moving slowest. So you know that geocentrically, the motion of the planets varies a lot. Heliocentrically, it's more constant, but it's not perfectly constant. And the higher the eccentricity, the more the speed changes. So there are two values that describe eccentricity. To summarize, what are the two values that describe eccentricity? One, how big is it? Mercury has an eccentricity 0.21, means it's very elongated. Venus has an eccentricity of, if I remember right, 0.01. It's very, very small, means it's almost perfectly round. So the size of the eccentricity and where the perihelion is. Or we could use the aphelion. But for now, we'll use the perihelion. Those two values describe the eccentricity. The perihelion tells us the direction of this elliptical orbit is 17 Gemini to 17 Sag, and 17 Gemini is the close point to the sun, and it's elongated by an amount of 0.21, which is a pretty large elongation. The only planet that has a higher eccentricity than Mercury is Pluto. Okay, and let me show you how the speed of Mercury changes. So when Mercury is in the middle of Gemini, at about 17 Gemini, it's moving very fast. Let me show you that in the Sirius software. Let's take, this chart, this is my chart, heliocentric. I selected heliocentric by going to settings, coordinate system, heliocentric, and let's go to time adjust, and I'm going to move backward until Mercury is in Gemini. So I'm just going back. There it is in the middle of Gemini at almost exactly 11 degrees Gemini. So what I'm saying, when I go forward one day, because Mercury is at perihelion, it's going to move fast. Let's see how fast it moves. From almost exactly 11 Gemini, it moves to 17 Gemini, 17. That's over 6 degrees. 6 degrees, 19 minutes. So it's moving 6 degrees, 19 minutes a day. Now, when Mercury's at Sagittarius, it'll be moving slowest. I'm going to add 44 days. Why 44 days? Because it takes Mercury 88 days to revolve around the sun. Remember, we're doing everything heliocentrically. Now let me move back one day. So here I am in the middle of Sagittarius, 14 Sagittarius 08. In one day, Mercury moves to 16 Sagittarius 52, less than 3 degrees. Again, that's 14 degrees 8 minutes to 16 degrees 52 minutes. It's about 2 2/3 degrees, less than 3 degrees. So Mercury is moving more than twice as fast. It moves from less than 3 degrees a day to more than 6 degrees a day. So less than 3 degrees a day when it's at its aphelion. Whenever Mercury heliocentrically is in Sagittarius, moving very slow. When it's in Gemini, it's moving very fast. And in between, it's gradually changing. So it's just interesting, as astrologers, we're interpreting the positions of planets. It's nice to know how they're moving. Normally we do geocentric, but it's nice to know how the planets move. And there's 3 basic values. There's others, but 3 values we're focusing on here that describes how a planet moves. Number 1, how far it is from the sun. That's obvious. Second one is eccentricity. And how do we describe eccentricity? 2 values. How big is the eccentricity? Again, Mercury has a large eccentricity, 0.21. And what direction it is in. We can use the perihelion to describe that. That shows the direction in which it's elongated and where the planet is closest to the sun. And it's also where the planet is fastest. Now, I've added something to this image that I did not show you in the first video in this series, which is I added the outer planets. So we have the 5 outer planets plus Mercury. So Mercury, perihelion, is 17 Gemini, Venus 11 Leo, Earth 12 Cancer, Mars 6 Pisces, and here's Jupiter at 13 Aries, Neptune at 7 Taurus, Saturn at 1 Cancer, Uranus at 22 Virgo, Pluto at 14 Scorpio. This is for fall 1996, and again, these are the actual orbits. That's the actual size. That's a realistic image of what they actually look like. So the perihelion of the planets is kind of spread out, right? I mean, it's kind of spread out. I mean, there's some bunching up from Aries to Leo, but they're spread out, which means that the elongation of the orbit is going in different directions, right? You could think of it as like the egg of Mercury. It's kind of a crude terminology, but it's like the egg of Mercury is pointing like this, and the egg of Uranus is like almost square it. It's facing, in a very different direction. So they're not all kind of lined up in the egg shape. They're not all elongated. They're not all stretched in the same direction. It's just the way it is. So that's what it looks like. Okay, now the second thing, and this is the one that's directly related to latitude, is the inclination. So you know what eccentricity is, and we learned a little bit more about eccentricity there. It also indicates where the planet is fastest in its heliocentric motion. Now remember, Venus. Let me ask you a question before we go on to inclination. Will Venus's heliocentric speed change as much as Mercury's? I'll ask it again. Does Venus's heliocentric motion change as much as Mercury, or is it more constant? The answer is it's more constant. It does not change as much. Why? Because it has a smaller eccentricity. Its orbit is closer to round. The closer that the planet is to round, the less it changes. You know, Earth has an eccentricity a little bit larger than Venus, about 0.02. And the speed, what we call the apparent speed of the sun, so when we look at the sun, the speed of the sun is actually like an optical illusion caused by the motion of the Earth. If you're an astrologer, you may know that the speed of the sun in your ephemeris varies from about 57 minutes to 1 degree 1 minute, from a little bit less than 1 degree to a little bit more than 1 degree. There's some change of speed, not a whole lot. Why is that? It's because the Earth has a low eccentricity. If the Earth had even a smaller eccentricity like Venus, then the sun would be even more constant. And if the Earth had a higher eccentricity like Mercury, then the speed of the sun would change more. So it's the eccentricity that determines how much the speed of the planet varies. Okay, so now inclination, and this is the one more directly related. I mean, it's directly related to latitude. And inclination is the tilt of the planet, the tilt of the orbit of that planet relative to the Earth. And Mercury not only has high eccentricity, as I just mentioned, it also has high inclination, 7 degrees. But there are two values to describe inclination. So there are two values to describe eccentricity and two values to describe inclination. And those values for inclination are, number one, just like for eccentricity, how big is it? And the size of the inclination is the angle that the orbit makes to the orbit of the Earth, and that's 7.0. The inclination for Mercury is 7 degrees. Almost exactly 7 degrees, 7.0 degrees, which is more than the inclination of other planets, with the exception of Pluto, which has, its huge inclination of 17 degrees. And then what is the other thing, the other value that describes the inclination? It's the north node of the planet. So the north node tells you where the planet goes from being below the path of the Earth to going above. And you'll notice that the north node of all of the planets, I put all of them here in purple, and I put a dot for their, a little purple circle, little big dot here for their approximate positions. Unlike perihelion, they're bunched up. They're all between 18 degrees Taurus and 12 Leo. This means that all of the planets are at their lowest point down here in Aquarius area. So down here in Capricorn or Aquarius, when planets are in Capricorn or Aquarius, depending on which planet you're talking about, they're in their lowest part of the orbit, and then they're coming up, reaching the path of the Earth. They're getting higher and higher in Taurus, Gemini, or Cancer, and then they reach their highest point 90 degrees past the north node. So, just to make sure we know what we're talking about, let me go all the way back to our first slide that we saw in the first video in this series. Here's the path of Mercury, this turquoise blue circle here. And what this is showing is that Mercury has high inclination of 7 degrees. And when Mercury is here, where this black point is, it's at its north node. Mercury's north node is here. And up here on the right is where Mercury reaches its highest point. And Mercury is at its north node at 18 degrees Taurus. Mercury reaches its highest point at 18 Leo, back to its south node at 18 Aquarius, and it's at its lowest point at 18 Scorpio. So that's how it moves. Okay, let's go back to the slide that we're on, which is here. Okay, so that's how the planets move. That's their, you now understand eccentricity in some detail, and you understand inclination in some detail. Is there anything else here I need to talk about? No, this covers it pretty well. Okay. Okay, let me show you something in my own chart related to this. Here's my heliocentric chart. Mercury is at 11 Leo. Now, I know I'm throwing a lot of numbers at you, a lot of positions. 18 Leo, this is the heliocentric. I went over here to settings, coordinate system, and I selected heliocentric. So this is the heliocentric, my heliocentric chart. Going back to this diagram, Mercury's heliocentric north node is at 18 Taurus. That means that 90 degrees later at 18 Leo, Mercury reaches its highest heliolatitude. Let's see if it's true. My Mercury's almost at 18 Leo, and it's telling me the heliocentric latitude is 6 north 58. I'm going to go to time adjust. Go 1 day later. Now, 1 day later, Mercury is within 1 degree. It's at 17 Leo. 1 degree later, it'll be at the square, 90 degrees to the perihelion. It'll be at its highest point, and there it is, 7 north 0 0. When a planet is 90 degrees past its heliocentric north node, it's at its highest point, and that highest point is the inclination of the planet. Mercury has an inclination of 7 degrees, and there it is. If I go to the next day, it's gone back down. 6 north 59, and Mercury is now at 22 Leo. So when Mercury gets to that 18 Leo point, it reaches its highest point, which is 7 degrees north, and that is the inclination of Mercury. When it reaches 18 Aquarius, it'll be at 7 south 0. Okay, so there it is. Because inclination, let me just show you again. Let me go back to this first image. Here's the sun. So when Mercury's on this right top point, it's at 18 Leo heliocentrically. It is at its inclination of 7 degrees. The angle of the sun to the Earth's orbit, to the highest point of Mercury's orbit, is 7 degrees, that inclination. So there you see it. So just to get familiar with actually looking at these things and how they relate to the astrology chart, it's a little bit complicated because you have two things. You have the eccentricity, again, which is how stretched out it is, and you have the direction of the eccentricity, which again for Mercury is the perihelions at 17 Gemini. It's stretched this way. And then you have the issue of inclination. And it just so happens that for Mercury, its perihelion happens to be, just a little bit less than one sign, about 29 degrees past the north. No, but they're independent of each other. You have eccentricity and you have inclination. And so those two things are the basic description of how the orbit, what the orbit of a planet is, plus, of course, its distance from the sun. Now, Now we get to the geocentric part, which gets interesting. All of this is going to help us appreciate what goes on geocentrically. From the Earth's point of view, here's the 5 inner planets. Here's the Earth, this blue circle. From the Earth's point of view, the latitude of the planets is different from what happens heliocentrically. And what happens is this. This diagram has a lot of information on it, and I've separated it out into separate slides. But what this diagram shows is the sun at the center. There's that Mercury orbit in that blue turquoise color. And then Venus, Earth, Mars. And what I've done is I've put the planets, Sun, Mercury, Venus, Earth, Mars, on the right side. And we're going to look at these one at a time so we can understand what goes on here. Okay, I put a green circle around the planets, lined up in the same direction. There's Mercury a little bit higher, and then Venus is pink, Earth is blue, Mars is red. Okay, so Mercury, Venus, Earth, Mars. And I've got 2 dark black lines. I have a dark black line going from the sun to Mars and from the sun to Earth. And what this shows is that one black line, like I just said, goes through the Earth, the dark blue. The other black line goes through Mars. And what is this angular distance between these 2 black lines? What is it measuring and how big is it? It's measuring the inclination of Mars. What I've done is we're assuming that these planets are at their maximum. If Mars is at its maximum height here, then this will be 2 degrees. So when Mars reaches its maximum height, it's 2 degrees above the Earth. It's about 2 degrees, actually slightly less than 2 degrees. This is its highest point in its orbit, and that's also the inclination of Mars. So heliocentrically, it's 2 degrees. Can you see what's going to happen from the Earth's point of view? We'll see this, I think, in one of the next slides. Okay, we'll get to it. Before we get to it, this is showing us this is a graph of the latitude of the planets. I can show you how we select this in the Kepler and Sirius software later, but this is showing us the heliocentric latitude of the planets. And look how beautiful it is, just perfectly wavy, like a perfect sine wave kind of thing. The red is Mars. So the heliocentric latitude, very regular. This green one is Venus, and it's, very even, very even. And Mars is going up to a little bit less than 2 degrees. This is very small, no doubt for you, but this says 0, this says 4. So this gray line up here is 4, and this gray line down here is 4. Notice that Venus comes just below 4 degrees, and Mars goes to half of that. And if we go all the way back, I'll do this real quickly, we will see that Venus's inclination is 3.4 degrees. Mars's inclination is 1.8. So we'll call Venus 3.5, Mars a little bit less than 2. And when you go into the Sirius software and you select the graphic ephemeris and you graph heliocentric latitude, which I did here from the year 2000 to the year 2020 for 20 years, there it is. Venus going 3.3 degrees, not reaching the 4, north or south, and Mars going to slightly less than 2. And all the planets are doing what they do. This line way up here is Pluto, which goes up to 17 degrees. It'll go way, way beyond the other planets. Okay, now what we're looking at is, excuse me, we're looking at the heliocentric latitude of Mercury. So now the black line is going through the blue Mercury, and that's the 7 degrees. This is just to show you that Mercury at its highest point in the orbit is bigger than Mars. And by the way, there's something here that's not astronomically correct. I've shown them all in the same direction. The highest point of a planet's orbit, they're all in different directions. I've just done this, put them all on the right side so you can compare. So this is just showing us that Mercury has a higher latitude, maximum latitude. And here we've included Mercury, and this is the graphic ephemeris of the heliocentric latitude of the planets, and there's Mercury going up to 7 degrees. This gray line above it is 8 degrees, and this gray line below it is 8 degrees. So it's going to 7 degrees, exactly 7 degrees. Right along there. So there it is. You can see it as a graph. You can, it just confirms how this works. Now let's look at the geocentric. This is really what I want to get to. This is where it gets interesting. Here's the Earth over here. What's the maximum latitude of Mars? You can see that it's much higher. It's a bigger value. It'll go 7 degrees. It'll go very, very high because the Earth is closer. From the sun, it's only 2 degrees. But if this Mars is opposition to the sun when it's at its highest point, its geocentric latitude can be larger than the heliocentric latitude. I said 6 degrees. So what happens is that we'll learn why, but this is what happens. What I want you to look at, and then we're going to stop here because we're at 27 minutes, and we'll continue with this in the next video. And this gives you something to think about and digest before we jump back into this. Look at this weird, wild-looking red wavy line. This is the geocentric latitude of Mars. It's kind of interesting. Notice this big dip. You see this big dip here? This happens to be around the fall, or it's between, it looks like it's late 2003, roughly, somewhere in there. So this is done from 1995 to 2025. This is a 30-year graph. So over 30 years, there it is, 1995 to 2025. And every once in a while, twice during 30 years, Mars makes a sudden dip down to 6 degrees south. On very rare occasion, Mars will go to 6 degrees south latitude twice in 30 years. Over here in 2003, and over here looks like late 2018. 2003 and 2018, Mars makes this sudden dive down in latitude. And I will show you in the next video why that happens. And notice its maximum north latitude only goes to a little over 4. Only one time or twice it goes above 4, and a few other times almost to like 3 to 4. So it'll only go to about 4 north, but 6 south. Isn't that weird? It's not symmetrical. Mars can go to 6 south latitude, but only 4 north latitude. In the next video, I will show you why. And it is kind of fascinating, this shape. I mean, if you just think about the red, look how it dips down, does a sudden dip. And notice how it comes to like these peak points. Like it's kind of round at the bottom and peaks up. and then peaks and then it peaks down. It like gets round at the top. See, here it's round at the bottom. It's like a mountain peak, like a volcanic peak, and then round, and then it starts rounding at the top and peaking down. You see what I mean? It's like round, round. Now it's peaking, coming to a sharp point, and look at this one when it goes to 4 north. It's round at the bottom and then comes to a sudden peak, another sudden peak, and then gradually starts becoming round at the top and peaking down. So it's kind of interesting how it gets round at the bottom, goes to a high north peak, and then becomes round at the top and goes to a sharp south peak, and the south peak is greater than the north peak. Mars goes to 6 south latitude, only to 4 north latitude. So my point is this. Mars latitude is very different from this. Heliocentrically, it's just this very simple, perfect, nearly perfect, like sine wave, just all the planets going like that. But geocentrically, it's very interesting. And we are going to learn in the next video why Mars makes a bigger dip south than it does go north. So it's interesting. This is just what the planets do. These are things that, hardly anybody has noticed in astrology. Astronomers don't talk about it much. It's, not, they just don't for whatever reason. But to us astrologers who are interested in how planets move and that these things might have some relevance, does this rare occasion when Mars goes all the way down to 6, extremely rare event, only twice in 30 years, it's interesting. We'll talk about it later on. We'll talk about what it means. Okay, well, that's it, my friend, for the second video. We will continue with this in the third video in the series. Thank you very much for listening. God bless. Namaste.